give this as the input to all the points, right? And we already know that each point has got a set of weights, right? So we'll just find the Euclidean distance between the points, each of the points, with this given input, and whoever has got the least Euclidean distance wins. So if I give a random square 30 by 30 image to this, all these points will compete, and the one closest to that given input, closest being the nearest in terms of the Euclidean distance, wins. So there is always competition in this lattice, and the training happens such a way that when I give this first square, right, the first feature map square, the first point will always win the competition, and not just win, it should win with a good margin. The margin being, out of 30 by 30, which is 900 degrees of freedom, the point should win at least by 825, which is not a small number, right? Which means this point and the first degree of freedom of this point, right, should be the closest to the corresponding corresponding point in the feature map than the other points. So that's how you win in 1 degree of freedom. I hope I made it clear. Anyway, I'll explain it again if things are not clear to you again, right? So this is the point, and this guy is supposed to win when I give this as the input, this square, the feature map square, right? So this guy is supposed to win, and if he has to win, he has to win not only by being the closest in terms of Euclidean distance, but also he has to win along at least 825 degrees of freedom out of the 900 available ones, which is not an easy thing to do, right? And when I give the subsequent square, say this square which I have drawn, I have highlighted here, the square, say if I given this square, this should be the point that wins, and again by the same margin, 825 degrees of freedom out of the 900. So you can imagine the training is primarily based on the degrees of freedom and the Euclidean distance, and it is not simple, there is so much of competition among the points, and there is so much of computation required to make one point win among all the points, and not only that, by the margin 825 degrees of freedom. So it is, but the idea, but the use, but the actual effect you get is you have a powerful solution for your fingerprint recognition authentication problem, because you just need to give a particular square which is 30 by 30 out of the 80 by 80 image to the lattice, and if the lattice And if the lattice after taking this input wins in one point, and that too with at least 825 degrees of freedom, which means you have a wonderful fingerprint recognition software, right? Because I don't have to give the whole image. I can just give a square in this image, and I can easily find out if that is the image that was used to train the self-organizing map here, the lattice. So we have a powerful solution. We don't need to look at the ridges, the curves, right, to find out if this fingerprint is actually the one that I have, right? The usual conventional methods of fingerprint authentication are you might have seen. It's basically look through the fingerprint and look for ridges and bifurcations, right? You have bifurcation here, and you have a ridge here, you have bifurcation here, right? So well, it's a good method. I'm not saying it's a bad method, but we could do better, right? There are just few ridges and bifurcations in this fingerprint, but there are so many dots in them that are very much the part of a fingerprint, right? Every dot here, every curve, everything is a fingerprint, is part of the fingerprint, and all have to be considered. You just can't look at the ridges and the bifurcations. There are some of them that look at the directional vectors of a fingerprint and try using them for authentication. Well, that's again, you look at direction, but given a human being, when he's given a fingerprint, right? So this is the solution that I have created. So let's do some math here, shall we? We have some calculations done, right? So the degrees of freedom for a point, it is 30 into 30, which is 900. Required number of degrees of freedom to win for a point to be successful is 825. Alright, so let's see the probability of a point winning. It is 1 by the number of points to the power number of degrees of freedom, which is let's look at this first. We have 1 degree of freedom here, right? This fellow of this point. So the probability that this guy wins is 1 by the number of points, because each point will have the corresponding degree of freedom, and this point is supposed to win among all the degrees of freedom in all the points, right? This point is supposed to win, this fellow, this particular degree of freedom is supposed to win along the same degree of freedom in all the points. So it is 1 by 51 into 51, which is 1 by a big number. Now, what is the probability that a point should win? Well, a point wins when there are at least 825 degrees of freedom 1 in a point, which means 1 by 151 power 825, which is 1 by a big number. So the probability for your point here to win is unimaginable, right? So it's a big number though. So this is the probability calculations if you want to see. You might ask, well,